So yeah, I'm doing my PhD, as I've been introduced, as in atmospheric physics, and specifically I'm looking at stratosphere-troposphere coupling. And you might have heard of the fact that the atmosphere, like ogres, like onions, has layers. And each of these layers has quite distinct dynamics. And the layer which we live in, the troposphere, is just one of them. And I'm going to be talking to you about the layer just above that, which is the stratosphere. And sort of talk you through what I'm going to be talking about. I should probably say at the start, this is real physics, right? A lot of people dismiss this kind of thing as geography, but the study of the study of the atmosphere is ultimately the study of a physical system. It's the greatest experiment on Earth. You know, it's a combination of physics and maths and chemistry and a little bit of biology. And in order to understand what's going to happen in the future, we need to apply physics to what's happening now. So that's what I'm going to start talking about, basically introducing the kind of physics that we use. And then specifically which particular part of physics makes the stratosphere the way it is. And then what happens in the stratosphere, which is ultimately tens of kilometers above our heads, can directly affect what happens to us at the surface. So, well, let's get started. The atmosphere, you might have heard of it. It's quite useful. It keeps us alive, keeps us warm. To give you a sense of what kind of physical system we're dealing with, it's actually quite difficult to describe where the atmosphere stops, because the density goes exponentially with height. So you have to reach a cutoff point where you say, well, that's enough. There's not really enough molecules for us to call it an atmosphere anymore. One definition is 600 kilometers above the Earth's surface. That's the point at which the radiation constants, when you hear people saying there's so many watts received at the Earth per square meter, that's where that's expressed. It's also the top of the thermosphere, which is another one of the layers in the atmosphere. But that definition is a little bit tricky because Mir, which you can see here, I think that's Mir, right? Yeah. And the International Space Station, they both orbit about 400 kilometers above the Earth's surface, so well within the atmosphere by this definition. The space community tends to prefer a definition of the Kármán line, which is 100 kilometers above the Earth's surface, and that's above the mesosphere, which is the layer above the stratosphere. And that's sort of, if you want to think about the atmosphere in terms of how big we're dealing with, that's a pretty good estimate. It's a planetary system, about 100 kilometers tall. Compare that with the Earth's radius of 6,400 kilometers, and you're dealing with a very small fraction of the size of the Earth, and yet it has a massive difference on our lives at the surface. And even that 100 kilometers, I should point out, because it goes exponentially, it's really only the very bottom 10 to 20 kilometers that actually has a noticeable effect. So if you were to have a globe of the planet, the atmosphere is the thickness of a layer of varnish that you might put on it. It's a very, very thin system. I can tell you what it's comprised of. It's mostly nitrogen, a bit of oxygen in there, thank God. But the point is it's a fluid, right? We describe the physics of the atmosphere as a fluid. So we use the same equations that we use to describe water or oil or pitch. And anybody here who's taken the third year course in fluid mechanics will recognise that's the Navier-Stokes equation, where V is the velocity vector, and you've got the density term, the pressure term, dynamic viscosity, I think, and then this is a forcing term, which includes the Coriolis force, which is obviously very important on Earth because the Earth spinning lends it an awful lot of dynamics, which you just wouldn't get on a non-rotating planet. And the system is thermodynamical. All energy on the Earth derives from the sun in one form or another. And so in order to derive the system, I've just used the first law of thermodynamics, but we have to use an understanding of thermodynamics. So for anybody who hasn't taken the second year course in thermodynamics, this is just saying that the total energy change in the system is equal to the heating plus the work applied. So work, for example, might be if you had a piston of air and you compress it, that's doing work on the system. So that's basically the system in a nutshell. It's only 19th century physics. It's pretty easy. You know, why is it so hard? Well, it's very hard because it's a very complicated system. Nobody solved the Navier-Stokes equations exactly, for one thing. So we don't have a general solution to the atmosphere. And also because it's a chaotic system, meaning that if you have a small measurement error in one of your measurements of, say, wind velocity or temperature, you can't predict more than 10 days in advance. You know, it doesn't matter how powerful your computer is. Because it's a chaotic system, anybody, again, who's done the third year course will know this, your predicted future will be massively different from the observed future. So, the section of the atmosphere that we live in, I said before, is called the troposphere. And it's typified by the fact that, it's defined by the fact that when you get higher up, it gets colder. You know, if you don't see people climbing Mount Everest in flip-flops and Hawaiian shorts. And I always found that a little bit paradoxical as a kid, this idea that when you get closer to the sun in the day, it actually gets colder. But the fact is that the air above the Earth isn't heated by the sun, it's heated by the Earth. So, in simple terms, the sun emits shortwave radiation. It's a very hot body, so it emits an awful lot of energy. And it does that in high-energy photons, so short wavelengths. The atmosphere is basically transparent to this kind of radiation. It doesn't absorb any of it. The fact that certain substances absorb radiation at certain frequencies is determined quantum mechanically, and that's just a whole lecture in itself. You just have to take it on trust that because the air is nitrogen and oxygen for the most part, it doesn't interact with this shortwave radiation at all. What it does interact with is the longwave radiation, which the Earth gives off. So the Earth will take in this energy and it will re-radiate it, but because it's radiating at a much lower temperature than the Sun is, it radiates it as longwave radiation. There's less energy coming off. And this energy is then absorbed by the air mass above the Earth. So if you take this cubic meter of air above the Earth, then the radiation which is coming into it, it will take a certain percentage of that because it's not completely transparent. And then what's left will pass into the next cubic meter of air above it. And that keeps happening. And every time a cubic meter of air will absorb some of that radiation, the signal is attenuated. So you get less heat propagating up through the atmosphere. So because there's less energy going into each cubic meter of air, it then re-equilibrates at a lower temperature. So, if you have I've always wanted to do this. I don't actually need to do this, but I sat through so many second-year lectures, I just want to draw on this board. So if we have height there, and temperature. Oh, it feels so good. Then at the surface you have a certain temperature, and then it decreases up until a certain point. But it doesn't keep doing that, because in the stratosphere, it starts doing this. And to give you an idea of how much this temperature change is, at the point where the temperature stops decreasing as you get higher up, it's about minus 50 degrees Celsius. It's actually pretty cold. And we call this point the tropopause. This is the boundary between the troposphere and the stratosphere. And by the time you get to the top of the stratosphere, it's about 0 degrees Celsius, maybe minus 5 degrees Celsius. So it's a significant amount of heating. So, what's causing this? Well, I said before that the atmosphere is transparent to shortwave radiation that the sun gives off. And that's true for the most part, because most of the atmosphere is diatomic molecules. It's nitrogen and oxygen. A significant factor of the stratosphere that's not diatomic is ozone. Now, ozone, for those of you that don't know, is just 3 oxygen atoms stuck together, and it's formed by when a very, very high energy photon will strike into diatomic oxygen, split it apart, and they'll combine with other molecules. And ozone will absorb high energy photons if they're UV. You've probably heard of ozone because of the ozone layer, right? This idea that we've been destroying the ozone layer with CFCs, and by doing that we get more UV radiation at the surface, and everyone dies of skin cancer. Fortunately, this is actually a great success story. No one reports the fact that the ozone layer is actually healing itself quite nicely because the Montreal Protocol passed and we stopped polluting the atmosphere. But what happens is this ozone will take in one of these photons, these UV photons, and it will split it into atomic oxygen and diatomic oxygen. And in doing that, it gives these two products more kinetic energy than the ozone molecule had to start with. So you get these two more dynamic molecules, or atoms, really. And the macroscopic effect of more atomic motion is an increase in temperature. That's all temperature is. It's, the macroscopic effect of a microscopic motion. And so this heating effect drives this change in temperature as you get higher up. Now this means that the stratosphere has very different dynamics to what we experience on Earth. Well, and our experience. I actually do need the light bulb. So, let's consider, this is just a basic bit of thermodynamics. So let's say that we have two layers in the atmosphere, and they're at T2 and T1. And we use the ideal gas equation, so I'll just write it in this form, that the pressure is equal to the density multiplied by the molecular gas constant multiplied by the temperature. But I'm going to rearrange it for the density of the gas, so P over RT. Now, let's consider an air parcel at this temperature. And when I say air parcel, what I mean is like if you were to just have an infinitely thin balloon, and you were to blow it up in that bit of the atmosphere, and it had exactly the same pressure and density and temperature, and it's just a convenient way of sort of holding on to a particular bit of air. And let's say that this gets displaced upwards. And this could be by a plane moving through, and it pushes it out of the way with its wing. It might be that it's bumbling along, and it hits a mountain, and it gets pushed up. It doesn't really matter. But let's say that this gets moved up to this layer in the atmosphere, T2. But it's still at temperature T1. Now, let's say we're in the troposphere. Let's say that this is up some mountain somewhere. And the density of this air parcel is the same as it is down here. So its density is the pressure divided by R times T. And because the temperature is higher at the original position, that means that its density is less than the density of the air that it's been thrust up into. Right? What this means then is that you've got a fluid with less density surrounded by a fluid with a higher density, in exactly the same way that if you were to blow an air bubble underwater in a swimming pool, that bubble rises up because it's got less density. This happens in the atmosphere. This is going to keep shooting up. There's nothing to stop it until it hits the tropicals. And this is what gives the troposphere its name, tropos, Greek, turning. It's dynamically unstable. Now instead, let's consider what happens in the stratosphere. So if we do this exactly the same thing, we displace this air parcel and we put it to this new temperature, except this temperature is now higher, which means this is an air parcel which is denser than its surroundings, because of the inverse dependence on temperature. So what this now does, it goes back down. It descends back to its equilibrium position. And exactly the same thing happens if you were to descend it, if you were to push it back down again. The stratosphere, stratos, is stratified. It means that it's very boring, dynamically speaking. Well, actually, boring is the wrong word, but it's completely different from what we experience on the surface. And we can see how different by a really cool website I found called earth.nullschool.net. Where's my thing? And this website visualizes climate data in real time. So this is a map of the Earth's velocity, wind velocity right now. And you can do this with different variables. So you can look at temperature and pressure. So you can see that we've got you can see that we've got depression here. We've got a depression here. Finished. We've got a depression there. We've actually got two depressions there, and you can see the flow cycling around it. And we can click and we can have a look at what the wind velocity is like. So that orange bit, that's 92 kilometers per hour just off Scotland. And you can see there's a lot happening, you know. There's some interesting thing happening just below Sicily. There's something happening over Russia. There's something happening over North America. There's a lot going on, right? Now let's zoom out. And the other cool thing about this website is it lets you look at the atmosphere at different layers. So this is the troposphere. This is the surface. Let's look at the stratosphere. And you'll notice, by the way, this is in pressure. People define things in the atmosphere by pressure rather than height. It's just a convention. It looks very different. Let's have a look. So, remember, it was the orders of tens of kilometres per hour over Scotland. How fast is it here? 356 kilometres per hour. This is the polar vortex that everyone's heard loads about. And this is the defining feature of the northern hemisphere winter circulation in the stratosphere. It's much simpler. You get these big growth structures. And this is only in winter, by the way. If we look at the southern hemisphere, where it's obviously summer, bugger all. Although, yeah, you get this big sort of zonal circulation going on. So, it's very, very different. And because the atmosphere is so thin up there, it was long assumed to be basically like an add-on to the troposphere. It was forced by the troposphere. You know, things like planetary waves that are caused by mountains and whatnot will propagate up there and they do something. There's something called the quasi-binary oscillation. It's a big deal over the equator with bands of descending wind, but that they don't go into the troposphere. And so it wasn't really until the 1950s and 60s that people actually started wondering, maybe the stratosphere actually has something to do with what happens on the surface. So how could the stratosphere affect the surface? And there's a few ways in which it can do it, and I'm only going to talk about this briefly. You can ask more questions if you like. These are mass exchange, planetary wave reflection, which is unfortunately not quite as cool as it sounds, induced mean meridian circulation, which is way less complicated than it sounds, and descending vortex anomalies, which is what sort of my research is in. So the first one of these, mass exchange, this is a figure that you see absolutely everywhere. Now what we're looking at is the position of the tropopause. So you remember that the tropopause is this distinction between the troposphere and the stratosphere, right? So the difference between these two regimes. And that's the thick lower line there. And it varies as a function of latitude. So for the equator, it's actually quite high. And that's because the equator gets more radiation with the Earth spinning. That's where it's most felt. And it goes down to about 7 kilometers or so at the poles. This grey region is areas where the technical definition is it's areas where lines of constant potential temperature intersect both the stratosphere and the troposphere. What it means is that air masses can flip between the two because mass movements are conserved on these surfaces, and because they intercut both the stratosphere and the troposphere, you can get matter moving between the two. And this was discovered in the 50s and 60s because of a very morbid reason, and that's that both Soviet and American scientists wanted to know if you detonated a nuclear warhead and blew loads of radioactive matter and fallout into the Earth's atmosphere, If you blew it high enough into the stratosphere, could it go all the way around the world, go back into the troposphere, and then land on your city? And that was, if you look at these papers, it's horrifying. I did a search on all these papers in the 50s and 60s, and it's literally just in the title, like nuclear fallout in the stratosphere, and working out whether it will come down to the surface or not. That's one example. Another example is ozone. So I said that there's this ozone layer in the stratosphere, which is what causes the stratosphere to have its dynamics. And ozone, unfortunately, has some sort of rather unpleasant health effects if you breathe it. Apparently it smells like magnolias, but it causes you sort of respiratory... Actually, you're a doctor, Joe. What does it do? Oh, okay. Some doctor. Yeah, it causes some unpleasant effects, and it's what happens when you get smog, get photolysis. So in Los Angeles, one of the big problems with smog is that UV radiation hits it, and it causes ozone to be formed. But equally, stuff which kills ozone makes it from the troposphere into the stratosphere. So the CFCs I was talking about before, this is sort of how they move across. The next thing, planetary wave reflection. I promised that this is a bit less cool than it actually sounds. What we're looking at here is the jet stream. So this is the pattern midway through up the troposphere, which sort of dictates where a lot of northern hemisphere weather goes. And it's an example of a planetary scale wave. It's an oscillation in wind, as you're going around the atmosphere. And these waves don't just propagate horizontally, they also propagate vertically. And what happens is they hit the tropopause, and they're reflected, or they can be reflected. And what determines how much is reflected and whether it gets reflected at all is the shear that happens here, so the difference in velocity between the stratosphere and the troposphere. So this was only considered in the 80s. This is really, for physics, that's very, very new, I'm sure you know. And what happens is these waves then propagate up, they bounce off the top of the troposphere, and they re-interfere with themselves. So you get much more complicated dynamics. It's a source interfering with itself, which is sort of a bit odd. Right, okay, next one. Induced mean Rhydian circulation. I'm going to get that right one day. This is a little bit drier, but it is kind of cool. What we're looking at here is this grey region this is a theoretical solution. This isn't actual data, unfortunately. It's basically, if you had a small room and you turned a fan on at the top, what happens is you get a circulation forming, right? And even if there's even if you were to distinct the two layers of the room, it doesn't matter. There's going to be some small level of circulation going. And that's what this is basically talking about. Those planetary waves I was talking about before, they propagate up into the stratosphere and they break, like waves on a beach break, and they deposit momentum. On a beach, the momentum is deposited into the sand, and it causes the sand to move around. In this case, this is a frictional forcing. It's a westerly forcing. And what we're looking at here is a meridional circulation. So when I say that, that meridional circulation is if that's the Earth, this is a meridional circulation. I like to sort of Hadley cells and Bell cells, there. It's zonally symmetric. And it's a very weak effect, but this ties in with before. This mixes matter between the troposphere and the stratosphere. And again, this is from a paper in 1995. This is really quite recent by physics standards. But most recent of all is the work which sort of I'm looking at, which is these descending vortex anomalies. Now, this is a really cool figure that my supervisor, Mark Baldwin, did. And what we're looking at is he averaged the dynamics of the polar vortex, that big swirling pattern that we looked at, and considered the anomalies in that, so when it was particularly weak or strong compared to average. And looked at what happened when you get these very, very strong, very, very weak vortices. What happens is, all of a sudden, these zonal wind anomalies propagate down, and they hit the stratosphere and the tropopause, and they keep going down to the surface. Look, this event happened at day 0 here, and it's still having a noticeable effect on the surface after 60 days. This is sort of one of the open questions. We don't know what's doing this. We can statistically look at what's happening. We can actually look at spatially the temperature effect this had. That was the wind I was talking about before. This is now the temperature. We don't know what mechanism is causing this, but it does give us a level of prediction. So I said earlier that you can't predict more than 10 days into the future in the troposphere because it's a chaotic system. With this, you can say that, for example, the top of the very north of Europe is going to be significantly colder than normal if you have a very weak vortex. And that's for 60 days. That gives you quite a long level of predictability that hasn't quite been maximised yet. This was 1999. Oh, sorry, no, the first paper was 1999. This one actually should be from 2002. And it's still an ongoing area of research. Because I often look at these talks and think, well, it's all nice and good you telling me this stuff. Why are you telling me if there's not a question at the end of it? These are the questions. We don't know what's causing that vortex anomaly to propagate down through. One theory that my supervisor has is that the strength of the vortex actually causes the tropopause to lift up, and it causes a pressure anomaly which then descends down to the surface. And that's sort of what I'm looking at. Once I actually get my program to work, that's what the code's supposed to be doing. It's supposed to be analysing pressure anomalies in the atmosphere. Other questions: how can we use that to improve prediction? Ultimately, there's no point in doing all this navel gazing unless it actually improves someone's life. And how will the stratosphere affect global temperature change? There was a whole chapter on this, I think, in the most recent IPCC report, because it's never really been considered, because the dynamics weren't really considered important to the surface. The fact that the stratosphere is cooling, because we've had less ozone because of the ozone layer destruction. The stratosphere has cooled whilst the rest of the surface is warmed. And there's a question of, well, what happens when the ozone goes back? Don't know. If you know, tell me. And equally, can we use the stratosphere to combat anthropogenic climate change? Who here's a fourth year, by the way? Anybody? Okay, there's a guy who will teach you in fourth year if you do the Atmos option, which you should all do because it's the useful one. There's a guy who will teach you who is involved in a method of combating climate change by injecting aerosols into the stratosphere. And because it's not overturning like the troposphere, you can assume that these things are going to stay in the stratosphere, and they'll then reflect excess solar radiation. And there's obviously a huge number of questions to do with that. I'm not an expert, but that's just saying. In addition to being this sort of roof on the atmosphere as we know it, might end up saving the day. But that is pretty much it, to be honest. I mean, I'd like you to take from this, A, the atmosphere has different layers, and they're dynamically very different. And that what happens, tens of kilometres, and hundreds of kilometres, in fact, away from us horizontally, has an effect on us. In exactly the same way, what happens tens of kilometres above us has an effect on us. And that, don't assume that our experience of the atmosphere is all there is to it. So, thanks for inviting me, and I guess any questions?